Rybkin. The title is Electronically Excited States, is use case for quantum computing, but I think it also feature kind of a robust discussion of kind of how electronically excited states play in spectroscopy and how they are calculated normally in quantum chemistry. So please.
Thanks, Michael. Welcome, everyone. Yes, as you can see, the talk was planned for yesterday, but it was as a introduction to Dmitri's talk, but now it's a postscriptum to his talk and to Michael's introduction to the use cases. Okay. Anyway, so it's more or less a chemistry talk in the world of quantum computing, and I'll try to introduce the use case as seen by chemists and maybe by industry a bit. And so why electronically excited states are a use case for quantum computers? So it should meet two requirements as any use case. So first, it needs to be useful. It's a use case. So someone needs to want to compute it. And second, it should provide some promise of achieving quantum advantage, at least in principle. Yes, it shouldn't be a data shuffling task. So, and let us immediately go into business questions. Yes, so that's how the probably cheapest spectrometer, which measures electronically excited states, so electronic transitions, look like, and you see it costs 250 euros, 51.99. So you can easily buy it and measure something as what is shown here, like electronic spectra. So if you remember yesterday's talks about NMR, you can see a drastic difference between simple electronic spectrum. So this is actually not just electronic, but ultra violet visual spectrum. So like that's colors which you more or less can see with your eyes. And the detailed structure of the spectrum is not much different from what we see. It's just, it's a molecule like this in the solution, and pH is a measure of acidity. So you add acid, and then it changes structure. So protons stick somewhere here, and then you see that as pH grows, you get this peak growing, and when you remove it, then you see these two features, essentially like two. One feature here, one feature there. So if you remember the NMR talks, like the level of details here is nowhere near, absolutely nowhere near. And from here to here, yeah, no way. You can't take the structure of molecule from this type of spectrum. Absolutely, no, never. Although this is something like this, a very cheap thing in solution, and one can get more detailed spectra, which I'll show later. But even they need to be informed by theory, highlighted in red. So, this is also my birth trauma as a chemist. So when I did my bachelor's in a that time cheap and poor university in the province, it had a lot of excellent organic chemists which were making molecules like this or larger molecules, and they had no NMR spectrometer actually. And so they had to characterize them with this. And like all physical chemists were making face palms on this all the time, yes. So what can you see from this? Only, like how your spectrum changes with pH, yes, is a useful information, but no structure available there. So the poor guys and ladies couldn't publish in good journals until they bought an NMR. I'm supposed to advertise the use case and not to bury it. So, the reason for it, is cheap. Even better spectrometers, which are powered with lasers, are also relatively cheap. They are cheaper than superconducting magnets, for instance. So it's still cheaper. It's fast. It's actually informative. If you know what you have, more or less, then how spectrum changes with pH is extraordinarily useful. Well, because it's color, by the way. So like color, this is color, everything is color. So for instance, textile industry, chemical industry is interested in colors. So you need to measure this. And also for quality control, if you know like what's in your solution, you can measure concentration of ions, for instance, like copper is blue, so you can measure this and say how poisonous your water is, whether you can drink it or not. So Therefore, I think it's a good use case because you can't just take structure from spectrum. You need to compute it somehow. You need to be informed. So there are chemists here, you know, and you may find the term electron spectroscopy strange because it's not what we are used to. So typically people talk about like photoelectron spectroscopy or electronic spectroscopy. So we are not pretending to have redefined spectroscopic methods in chemistry. It's our marketing term, which we use for actually electronic spectroscopy and photoelectron spectroscopy. What's the difference? So in molecules, yes, we have nuclei, we have in materials 2 electrons. So when electrons rearrange, we get electronic excitation. So states formed by electrons can be singlet, triplet, or depending on your multiplicity, something else, quintet, unrestricted. And this is done by absorption of visible light. Not necessarily visible, it could be also X-ray. And photoelectron spectroscopy is actually removing the electron by light. So you shine a photon on the molecule, electrons flies away, but these energies are typically in the same range. And this is also electron rearrangement. So why is it important here? So because, for instance, these type of transitions are very easy to detect. Most molecules are singlet, and singlet-singlet transitions are allowed by spin. Spin is the same as 0, so that's, you know, our standard colors. Triplet states, triplet first excited state, is typically lower in energy than singlet, so it could be more accessible, but it's not because this transition is spin forbidden. But this singlet-triplet gap, which Dmitry was also showing how to compute, is like not typically what you see. So relativity actually allows this transition, but very weakly. And actually to define this, we may go to this. By removing electrons, we can extract this. I will show this later. So, and also a bit on the terminology. So the key property we compute here now, because we have just started with this use case, is the singlet-triplet splitting. So ground state singlet, energy difference between ground state singlet and first triplet. So sometimes, very often, people define singlet-triplet splitting as difference between excited triplet and excited singlet, because this is very important for singlet fission, for singlet-triplet conversion in energy harnessing. But this is also important for, say, phosphorescent diodes. So first we compute this, but actually, as Dmitry showed to you, we can compute this, we can compute this, and we can compute this. Therefore, we compute this singlet-triplet splitting and these two, although we haven't focused on it yet. So you see, even for this model system of 2 orbitals and 2 electrons, there are many properties to compute, and all of them are relevant, in fact. But we focus on this first singlet-triplet splitting. So now a spectra of better quality, which actually theoretically computed. So, and a bit of definition. So this is a simple molecule, the carbene. For molecules of this, people got Nobel Prize because they are ubiquitous in organic synthesis. And it's a pretty simple molecule, 3 atoms, CH2. So how do we actually observe the singlet-triplet splitting? Because this is our ground state potential energy surface, so I'll just remind you that molecules don't only have electrons, they have nuclei. And in each electronic state, there is a potential energy surface in which nuclei move, and they also have quantized energy levels. So this is forbidden. We don't see it in the spectrum. So cunning people added electron to CH2 and then made photoelectron spectrum. So they removed electrons from CH2 minus and got a mixture of singlet and triplet molecules. And so by assigning the spectrum, they can get this difference. So, and that's a tricky part. So it's important to distinguish between adiabatic and vertical transition. So adiabatic means like average, like in thermodynamics, infinity slow. So from, in fact, this minimum to this minimum, and from this minimum to this minimum, or from this minimum to this minimum, from the minimum of potential energy surfaces, which we know they don't exist. Like molecule is never here because it has vibrational levels which are at least here. So this needs to be deducted from the spectra. And what one can observe is vertical, which is like from some vibrational state to the very same like vertical structure to a different state. But I know from here, the vertical line can finish somewhere here where there is no state at all. So what does it do? Instead, we get an ensemble of excited states. One is here, then another is here, and so on. And the intensity is overlap of vibrational wave functions known as Frank-Condon factor. And the more different the structures here are, the more complicated the spectrum is. So we see singlet states, an ion and a singlet are very similar. Therefore, we just get one line, which is from ground state here to ground state here. And for triplet, they are different. Therefore, we get a forest of lines of different intensities. So to get to a adiabatic, we actually need to understand what which line is, so which state, vibrational state it corresponds to, and then we go to 0, 0. So here to here, which is supposed to be the lowest energy one. Like here, it's simple, it's 0, 0. Although, we don't observe triplet and singlets separately. So they are combined and we have two forests in general case of more than 3 atoms. So we also need to, now we know this transition to this transition, but to go from minimum to minimum, we actually need to measure vibrations themselves, because this half of vibrational quantum is ground state of harmonic oscillator, which is kind of this difference. If you know the progression, then we can have this difference. If it's harmonic, if it's unharmonic, then it's more complicated. And that's nothing we can just take from spectroscopy. We need to compute it. So in our case, as we are still making first steps, we just compute singlet triplet gap. So this to this, in our case, singlet is lower than the triplet, molecules are different. And we do it just vertically. We take this minimum and we compute the vertical line. So it's nothing actually people directly observe, but it's close enough. And, we can make the theory more complicated, but sorry, one at a time. So animation didn't work out. So in the simplest case, the vertical singlet triplet state is just, the difference between this orbital and that orbital minus Coulomb integral between the two orbitals. So why do we need any quantum computing or even classical computing to compute this? Well, because in reality it's a very simple model, and a more realistic model is different. If you compute a single determinantal wave function for triplet and for singlet, then our orbitals will actually be different. They will not be the same, because these are different electronic states. And then, typically for singlets are, strangely enough, more complicated. You will have to consider more electronic configurations and mix them into your wave function. And not necessarily just 2 orbitals, but actually more. And the more, the better. Like when you add all of them, all orbitals and all possible excitations, you get it accurate. Then triplet is typically simpler, but you need a balanced description for both singlet and triplet to get a good difference, or at least error cancellation. And the requirements are different, generally. And this is a typical response of a classical quantum chemist to the problem. So you do a complete active space calculation. We select the most important orbitals, populated and non-populated, so occupied and vacant, and build Slater determinants out of all this and then solve it classically. It's plotted simple. We just take highest occupied, lowest on non-occupied. In reality, it's a subtle art of selecting the orbitals. Like there are chemists who made their career just by hand-picking the orbitals for right molecules. We do it differently. I will show it later, but it's a hard computational task, because already this complete active space scales exponentially. But if you want to do it actually not just qualitatively, but quantitatively, we need to apply dynamic correlation, as Michael mentioned, to this many determinantal wave function, which may become terrible. And here is actually our step transformed to quantum, but not only our step. If you read quantum chemistry works on quantum computing, you will see that from these active spaces, people start doing variational algorithms and solving them with unitary coupled cluster and things like that. So we know there are problems. We won't pick on this, so we propose something else, which we have already heard yesterday. And okay. These are things which Dmitry showed you yesterday. So these are the three molecules which he solved with boson, the spin boson model. And this is how we solved it classically. With multi-reference averaged quadratic coupled cluster, where we only took actually two orbitals as active space, like this and this. But that's not an ultimate solution, but a very good one, because molecules are simple. They are small. If you have more, we need larger active space. And you see, like these gaps will actually be used as reference in the hand-on session, which Dima showed the numbers were convergent to. So, and out of curiosity, I put the time in. So CASA CF, 5 minutes, MR AQCC, so quantum chemistry is a science with a lot of acronyms. You get like 2 orders of magnitude more for small molecules. See, if you want to go larger to something which I showed in the first slide, like you'll fail, you won't be able to do it. So that's why economic methods, also with promise for quantum computing, are necessary, or at least intriguing. So you can try to solve this without variational algorithms and with interesting bosonic physics in them. So it's actually an old presentation. Doesn't matter. So if you are curious about not hand-picking of orbitals, you can look at arXiv and find an active space, find a paper, so you can look at my surname and you'll find it. That's our classical answer. Sorry, a bit sick. So electron spectroscopy, just, you know, a minematic rule looks a bit ridiculous, but better to remember. That's not something you see in the textbook, but you see at HQS. So it's a marketing term which we use for electronic rearrangements. I think I have convinced you that it's omnipresent, especially every one of you can just buy it on AliExpress and experiment with yourself. But it needs theory. Therefore we are here trying to solve it. Conventional methods can be very accurate, but can be also very, very, very brute force. So quantum advantage is really desirable there. And yes, let us solve it. Thank you for your attention.